Hello friends, this is Dr. Sachidanand Singh, Faculty of Biotechnology. So, in the previous classes and previous lectures, we have understood about protein structure prediction and analysis. We tried to understand what are different protein structure prediction methods by experimental methods and by computational method. We also saw in protein structure methods there are different approaches like homology modeling, threading, ab initio. We also saw in previous lectures how protein structure prediction can be done using modular, in modular single template modeling and multiple template modeling. We also saw that how loop modeling can be performed for local areas to be redefined. In that, we also saw few n number of web based tools to have a user friendly application. We also saw in the previous lectures about Python scripts, and then we also saw some online user interface like Prosa, Geno 3D. For structure validation, we moved ahead with tools such as SAVS, Structure Analysis of Verification Server, and in that the basic concept was through ProCheck, Whatif and Verify 3D. So, now in today's lecture, the structure validation portion need to be done using Whatif. So, Whatif is a part of SAVS also, and it is an independent unit. So, in this lecture we will understand how Whatif can be used for structure validation, specifically protein structure validation. So, let us take in this lecture a brief explanation about protein structure and a detailed explanation about Whatif. So, what is protein? Protein are very simple molecules, they are linear chains of residues, and there are only 20 different residue types. So, let us see as a practice, we do definitely not understand the mechanism by which protein structures fold. Hence, the only forces that are used in the refinement of a new structure, that is a protein structure, are measured data and some facts that are well known for all molecules. No protein specific knowledge is used. Generally, the used information is not sufficient to find a unique structure. A large fraction of the refinement procedure consists of an expert looking at the protein structure and making a manual adjustments. Hence, protein contains thousands of atoms and it is impossible to keep an overview of everything that is going on by hand. These 2 points combined are the origin of incorrect structure and weak points in a generally known as correct structure. In everyday situation in a biocomputing or computational lab, a molecular biologist working on a big project to elucidate the function of a certain protein turns to somebody in a biocomputing group with a very specific question. And what is that specific question? I need a structure of that protein. Hence, they initiate a database search to find out what is known about the structure, and a very similar protein turns up from the protein data bank. In our previous lecture also we have understood about protein data bank, PDB. It is a kind of dream comes true to see the structure that can give an important conclusions to understand about protein structure. It is important to realize that any model based on the structure they found will be at least as bad as the structure or as good as the structure. So, should we use that structure or not? Should we take that as an alignment structure or not? It is obvious that structure that are very old might be of less accurate, because refinement techniques in 15 years ago were not so advanced. So, as a first indication, the years of publication can be used to see whether we might want to use the structure which was developed before, but this criterion is not very convincing to understand. Hence, refinement and validation is required. So, somewhat more sophisticated is to look at the resolution of the X-ray structure as well. The lower the number, the more data the crystallographer had available and more chance that any mistake would have been detected. So, the lower the resolution, better is the structure, but the resolution just gives you an approximate indication of how well the structure can be theoretically. It does not tell you anything about which part of the structure are good and which part of the structure are not good or cannot be trusted. It also does not warn you if there is a serious mistake somewhere. A lot more sophisticated is to use protein structure verification. Hence, for protein structure verification, programs like Whatif check menu can be performed. It will give us a detailed analysis of the protein, giving not only the overall number, but also specifying possible problematic residues. And it uses a graphical representation of results to get a quick overview of the structure. So, that is what the Whatif has been used. An everyday situation in a crystallography lab, crystallographers are refining a structure. They would like to know how they are doing. Is the overall trace reasonable, or is there a shift in this helix? Do all the geometrics look as expected, or are some side chains in strange conformation? Is there a good alternative conformation for backbone in this loop? Should they deposit a structure already? So, these all questions can be answered by using this structure validation tool such as Whatif. Hence, the crystallographer or NMR spectroscopist can use Whatif to check whether there are weak points in the structure, using the results to improve it before the deposition into PDB database. The big advantage is that he or she has the original X-ray data available and is still working on the refinement. To correct problems at a larger stage would be much more difficult. So, how this all started? This all started none the other, but it all started of correction of the errors in secondary structure level by G. N. Ramachandran in 1963. G. N. Ramachandran, Ramakrishnan and V. Shashikaran wrote a paper about a graphical representation of the two most important backbones of a protein, which we have already seen in the previous lecture, that are torsional angles. They presented a simple theoretical model showing that in a phi psi plot, all residues are fairly restricted in their possibility. In phi psi plot, 4 quadrants are there, and there all the amino acids are restricted. This phi psi plot, later called as Ramachandran plot, it was the first serious verification tool for protein structures. Structures that were solved before 1963 were solved without the knowledge of Ramachandran's work, and thus the Ramachandran plot can be used as an independent judgment of these structures. In later structures after 1963, the crystallographers would become aware of their work and could use it to help during the refinement. So, in principle, there should not be any structure with bad Ramachandran plot that have been deposited after 1963. So, the structures before 1963, but after 1963 should obey Ramachandran plot. However, there are two reasons why there are still structures with strange looking Ramachandran plot deposited in protein data bank much later than 1963 also. Let us see why. There was until 1994 no automated check of incoming structures at the PDB. So, bad structures occasionally slip through. There is no good way yet of using the Ramachandran analysis during a refinement. If the original X-ray data are insufficient to determine the backbone conformation accurately, the final Ramachandran plot will always look strange. So, the need for different kind of verification tools was the hour of need. The last point in the previous understanding which we saw was to have a good understanding of online tool detection as well. So, hence representation of good refinement tool and verification tool is an important aspect on which Whatif came into a picture, SAVs came into a picture. So, this verification tool can be used for refinement purpose. if such a tool is widely used, it will improve the quality of the new structure and probably make structure solution easier. But it is also nice if some of the verification tool cannot be used during the refinement. These tools can later be used for an independent judgment of the structure. A number of such checks are part of Whatif. So, Whatif is a kind of protein structure verification venue. So, what happens there is, where the knowledge come from protein verification checks work by comparing structural parameters to standard values. So, in this some standard values are specified on the basis of homology, identity and similarity. These standard values can be obtained in different ways. What are those? The absolutely undisputed best way of getting knowledge about protein structure is by studying unbiased protein structures. However, there are only very few highly accurate atomic resolution structures, which are almost approximately 1.2 angstrom. Definitely insufficient to calibrate many verification tools, and even the atomic resolution structures that are available are not completely unbiased. So, unfortunately, this will stay something for the distant future. In many cases, Whatif checks compared to standard values, as they are obtained from 300 best structures in the protein data bank. So, the structure which we submitted goes in the protein data bank, values all the most structures related to that, and it gives the result. This set is regularly updated and all checks are recalibrated. Recalibration is done once in a month. For some parameters, especially like molecular geometry like bond length, protein fragments are no different from small molecules. For these parameters, a calibration can be done using the Cambridge Structural Database known as CSD, a database of small molecule crystal structures. This is preferred over the 300 best proteins approach, as small molecule structures can be determined much more accurately than proteins and in almost unbiased way. Some parameters can be obtained from theoretical calculation, that is what Ramachandran et al. Did to obtain their standard Ramachandran plot. In general, however, these kind of calculations do not discriminate optimally between good and bad protein structures, because it is extremely difficult to design a good model. Understanding variations in numbers and standard, almost any number one can use to describe a structure which has some uncertainty. For instance, a single bond distance between two carbon atoms in a small molecule structure is about 1.53 angstrom, but some are bit longer and some are bit shorter. Say, most CC bonds in a small molecule structure are between 1.5 and 1.56 angstrom long. So, where does this variation comes from? Obviously, a bond between two, that is CBr3 or group of CCC, will be different from a bond between 2 CH3 or 3 CH3 CH3 bond. This is natural variation that is due to the fact that CC single bond does not completely specify the situation. This was the very first reason for variation in which was completely harmless, and understanding it will aid the understanding of the underlying principles of the structure to be refined or to be validated. The values can be inaccurately determined. In a small molecule crystal structure, bond distance are generally very accurate. So, if the real bond distance for a certain CC bond is 1.5 angstrom, the measured distance will be between 1.548 to 1.552 angstrom. This is the second reason for variation, which is not also again harmless. When considering the variation observed in a certain variable, it is of utmost importance to judge the influence of two mentioned effects on the variability. Looking at the example of small molecule, that is CC bond distance, the natural variation is much larger than the inaccuracy, and thus the variation observed. a normal CC bond length is between 1.5 to 1.56 angstrom, which is relevant. So, this is all about the bond length bond angle calculation. For a CC bond in an unrestrained protein structure, the opposite would hold it. The natural variation will be lower than for a small molecule. Because the variability in a local connectivity is much smaller, the inaccuracy in the determination of the bond length, however, is much larger than for a small molecule structure. The combination of these two differences makes the second effect much larger than the first, making the observed variation, that is a CC bond length in a protein is between 1.5 and 2 angstrom, absolutely irrelevant for understanding of the protein structure. Hence, the deviation can be understood by average and standard deviation. So, this explains now in Whatif average and standard deviation calculation for a protein structure. So, let us see what is average and standard deviation. Let us assume we have found a parameter that is worth studying. We have 1000 cc distances. We have a protein structure. In that protein structure, we have 1000 cc distances from a reliable small molecule structure. Any standard statistics package will tell something like the average is between 1.532, which we have seen, and the standard deviation of 0.021. What this tell us about structure with a 1.6 angstrom CC bond? So, let us take a look at a simulated normal distribution. So, when we will see a plot here, the plot here represents a histogram of an example data set, and it clearly depicts the normal distribution picture. So, what is there in this picture? We can see that any value that is within 2 standard deviation from the mean is completely normal. We can see in the figure itself. If we get further away from the mean, that is from the mean, if we move at either side of the mean deviation, it is increasingly unlikely to find the points. Less than 1 in 10,000 points are more than 4 standard deviations away from the mean. These ones we can call as outliers. So, if we get more outliers, the structure deviation will occur more. Coming back to our 1.66 angstrom bond, what we can say is the distance to the mean is from 1.6. If it is the mean, the distance from the mean is about 1.6 to 1.532. That means it is a deviation of 0.128 angstrom, which is about 6 standard deviations. This is highly unlikely and would definitely warrant further studies. We need to do more refinement. So, that was about standard deviation and mean. Now, let us do something similar for a protein. Let us say we have a 400 residue protein. For each of the bonds in this protein, approximately 4000. Now, we do an analysis like the one above, which we have done. Now, we find one that it is 4.5 standard deviation away from the mean. All others are less than 4.0. Is this the bond length deviation and error? Not really, because we expect 1 in 10,000, but here what is it? Is not that. 1 in 10,000, and to be more than 4 standard deviation away from the mean, and hence we studied 4000 numbers, wherein 1 in 10,000, keep it in mind. One deviation seems to be allowed here. On the other hand, what makes this one bond so special that it wants to deviate more than all other ones? This indicates a fundamental feature of a protein structure verification. It is completely normal to find a few outliers. So, there will be few outliers, which is a completely normal, but that also can be refined, but more outliers will give more of refinement at the further step, but it is always worth investigating them. But if outliers are not exceedingly rare, there is something strange going on. So, now in this standard deviation and mean, there is another very good feature which we also saw in a PROSA one is Z score. So, what is Z score now? Let us go ahead with Z score. Z score can be noticed that we need the phrase standard deviations away from the mean quite a lot. Mathematicians hate repeating along phrases, and they have given this new name. The number of standard deviation away from the mean is called z score. Formally, z is the measured value minus the mean divided by the standard deviation of the population. So, very clearly we can see z score calculation when these all understanding is given, a high significant understanding result and paper publication comes out. So, let us see the formula. Z is equal to x mu minus sigma. So, z is the negative if the value of x is less than the mean, and z is positive if the value is greater than the mean. Now, what are outliers? Now, all values with z less than equal to minus 4 or z greater than 4. Whatif uses this criterion for lot to decide which values need to be listed. So, they have a standard value of minus 4 to 4 where this z calculation is done. And what is z? Standard deviation away from the mean. Z has a very nice property for doing statistics. This can help us to judge whether outliers are indeed rare or whether they are more or less outliers than expected. This property also explains the root mean square of a population of z value should be 1. So, for our hypothetical 400 residue which we were studying, so if for hypothetical 400 residue protein, number of bonds should be approximately near to 1. Whatif contains a number of these tests and will complain or will compile or complain if any of these values deviates from 1.0 in any abnormal way. This is normally a very sensitive indicator. So, hence summarizing this mean, standard deviation and z score, there is a z score and an RMS z score. A z score, or a z score should be 0, and most of the time if it is negative it means worse than the average, and if it is positive better than the average, and RMS z score should be close to 1.0. Sometimes any deviation from 1.0 is bad. Example, bond distance is increasing. In other cases, one direction is good and other direction it may be bad. Whatif will give a subjective annotation to indicate what is good and what is bad. So, that was a detailed statistical understanding of Whatif and how it has been used. So, let us now see the installation of Whatif and what output and how it gives us. Whatif will run on Linux machine, but be aware that it may be tested on only one of the two them. Whatif is also a part of ProCheck, where on the online server also it can be done. But we can see if it can be done on Linux or Mac system, it can be taken up through https://trackmacpros.org browser trunk/science Whatif port file. This is also present in, as we saw, in SABS as Whatif. So, when the Whatif has been installed, or in Whatif the PDB file has been given, or in SABS, now let us see how the Whatif works as a independent online tool or a independent model restored into Linux. So, there are subdirectories into that. In Whatif we have to give the PDB file, and now let's see PDB output file will be like dvn pdb out. So, this will give us an output as PDB out. Some persons or some scientists might only be interested in checking the DB file. They can skip the latest etc. steps and can directly go to get the PDB file as an output. So, after running Whatif, the several files in our directory will include like pdbout.txt, which is the Whatif result in ASCII text format, pdbout.txt file, which is Whatif result file in LaTeX format. The third one will be checkdb file, which holds all the warning errors etc. It is in a format that is easy to parse by other programs. So, let us see now the output of Whatif in different sections. In Whatif it gives in different section all the outputs. So, the Whatif output has been divided into series of section, each section dealing with certain group of topic. Section 1 and 2 holds a series of checks that test for things that can influence many of the checks to follow in the following section. If, example, the symmetry cards are wrong, they may check that rely on a correct calculation of the symmetry will fail. What check actually perform like a prodrug, which cannot interpret a ligand properly. Hence, ligand related checks will not work properly. Section 3 will hold a series on options that don't really check things, but that nevertheless can be very informative. This section holds, for example, very important. Section 3 importance is in consideration of Ramachandran plot. Ramachandran plot is the portion in section 3 which has become clear from the clearly days that ProCheck in Ramachandran plot is one of the best protein quality indicator. Other descriptive output in the secondary structure may be in the PDB file, such as 4NL is a PDB code. The secondary structure looks okay, like helix and strand have same length, and the percentage helix and strand seems okay. Obviously, unstructured protein do exist, but their structure will be, definition will need to be solved. So, these portions can be seen in section 3. What is in section 4? The section 4 holds series of coordinate administration checks. Unexpected atoms are listed over here, B factor is reported, and occupancies are checked for plausibility, etc. What is there in section 5? This section holds a series of nomenclature checks like valine, air, C gamma, C alpha composition, use of old fashioned atom names, or weird chain identifiers. Section 6 deals with geometric problems such as unusual bond lengths, bond angles, chiralities, tau angles, planarities, etc. Section 7 deals with very important torsional angles, rotamers, backbone, side chain conformation. Section 8 deals with all the bumps presented in the protein structure. Section 9 deals with packing and inside outside distribution consideration. Section 10 of the result deals with hydrogen bond, waters, ions, flips of amino acids as a mutational portion. And last and none the least, the section 11 represent all the references from how the output has been resulted. The last two section gives a summary of the global statistics in term of RMS Z score, quality score, normality score, and the reference quoted for it. So, add together from section 1 to 11, we get all these results add together. What are the output formats of Whatif? The Whatif program uses the famous SOSHU command to analyze the content of a PDB entry. Inside Whatif/WhatCheck, this content is called the soup, SOUP, because after a PDB file entry and a cup of soup both consist of water and protein. A PDB protein is what? A protein structure with water. That's what the command is soup. The only difference are the order and the taste. A typical resultant SOSHU command is something like this, which will be done for our protein or a structure. If it is a protein, we will use this command. If it is a drug ligand cofactor, we will use the command mentioned over here. Single from entity or a group of waters, it will be represented like this. If we want to talk about drug with topology, it will be represented like this. So, in the graphical representation, we can see how the amino acid with their numbers are being represented. So, we can see how with the asterisk point the command is being represented with the amino acid number. Now, let us see how it looks like. This is the header of a SOSHU output. First, the content of the soup was protein and water molecule is counted. This table is only produced when the debug flag is switched on. Normally, the asterisk 2 output is skipped. The first one is protein and second is usually skipped. This is the header of a real thing of the SOSHU command. Molecule 1 is a protein with chain with identifier. Say for example, a protein of 316 amino acid, the second protein is of 2 residues peptide with a chain identifier D. The third molecule is a C-terminal oxygen of chain E and it is attached to a lysine. There are few examples quoted in the help file also, which has been reported, and the narrow indicates that it is bound to something molecule 5 till 8 are single atomic entities. Together with the 2 C-terminal oxygen, they form with the 7 atomic entities mentioned in the top half of the output. DMS probably stands for DMSO and it is a drug ligand or a cofactor in the protein. So, these are some terminologies or example which can be done for the 1, 2, 3, 4, 5 as shown in the table. So, for these type of example as shown in the table, the Whatif will represent in n number of activity. The Whatif number of the last residue will represent it as a molecule. The PDB number of the last residue in this molecule will be represented. A short description of this molecule, the set name will be represented and will be given as the name of the user what it's been given. This set name is only relevant when Whatif is used interactively. Some notes regarding to PDB file also will be represented. After showing the content of PDB file, the Whatif of Whatcheck will be submitted and it will give you the brief overview about it. Whatcheck will also look for residues with a negative or a 0 residue number, and it will also look for consecutive residues with decreasing residue number. Whatif will identify in different sections as an output, which can also find some statistics about the use of chain identifiers, and it will also give us the chain identifiers in different chains and their different sections separately for A, B, C, D. If there are 4 chains, 4 sections will be identified. Nonetheless, SOSU table will also be compared and meant with the experimental data and the computational data which has been identified. In case ions or the different classifiers which we identified are found, they have the wrong chain identifier identification also. So, SOSU will also understand and they will be listed in a table. An ion if identified is said to have the wrong chain identifier if its chain identifier is the same as that of a protein, nucleic acids or a sugar chain. So, this all will be considered and will be reported into the SOSU command. This SOSU command can be explained by a 4-letter code or by the series of amino acids to understand this chain identifiers. So, let us take an example of 1ET1 and we can see all the amino acids and how the analysis and performance is done using this Whatif check. So, the table represented here is of that PDB code 1ET1 and all the PDB structure as XYZ axis has been reported. Now, how the Whatcheck will give us the result and how it is being interpreted can be seen in the table and the whole pictorial representation is shown. So, what is it interpreting is the box lists different warnings, a series of bond angles considered as unusual is listed. The table as we already saw before was star 1, star 2, star 3 will also be reported etc. and is not part of the output but added here to label the columns. It will give as an output as the first number is the sequential number of the residue in the PDB file. The second column holds the 3-letter code of the residue. This can be any 3-letter code used in the PDB and can include amino acids like cofactors, drugs, sugars, lipids, iron, water, etc. The third column in the table holds the residue number as given in the PDB file. In this case, the first residue of the chain could not be seen in the electron density, so that the first residue in the PDB file actually is residue 2 of the molecule. The minus sign after the residue number indicates column 4. Holds the chain identifier for the residue. So, each section will also represent column 5 holds minus sign. If this were an NMR structure, this column would hold the NMR model number. The column labeled 6 will hold the 3 atoms involved in this check. Column 7 will hold the observed value. Column 8 will indicate how many standard deviation of the value is present. and column 7 is away from the Whatif target value. So, out of this all we have understood about PDB structure file, if it is there, or in PDB structure with water molecule like as a soup, in a PDB structure with the ligand, in a PDB structure with a cofactor or a molecule. By all this we have seen different examples with table and figure. So, in conclusion what we say is Whatif is used as a independent tool or just like a SAVS, which is including Procheck, Whatif and Erat3D. So, Whatif gives a refinement and it gives all the results in sections. So, this was all about Whatif protein structure validation. So, in this whole lecture we have understood protein structure validation using Whatif, which can be an independent unit into Ubuntu or in SAVS server. Thank you.